Hi, I'm Alexis Stahl,
I'm Ralph Studer.
and this is our research on graph homotopies.
To start, we define a graph as a set of vertices and edges or connections between vertices.
We define homomorphisms as between two graphs where edges are preserved. So if there's an edge in the second, the edge must be preserved in the second, or in the first graph, it must be preserved in the second graph. So here you can see W moves to V, and since there's an edge between Vx, then moving W to V preserves the edge between W and X.
We define a spider pair as two graphs that differ by at most one vertex. So we can see in the example that these two graphs differ by one vertex, and that's U being sent to V, or V being sent to U.
So here we have another example where F and G only differ at V2.
So two homomorphisms are homotopic if there exists spider moves in between them. We can see an example that each of the antennas is folded into the vertex Y, and so therefore the identity G on the left is homotopic to the graph G on the right.
And we have the spider web of two graphs is defined as the vertices are homomorphisms and the edges are between two homomorphisms that are a spider pair. And we look at a spider nest, which is just a spider web of G to G. And then below here we have a graph G and we show its spider nest. And as we can see, if we do a fold or move C to A, we can see we get the vertice in the square that's on the right, the ABA. So we can see that when we fold it, we get a homomorphism of that graph, and it's ABA.
So a fold is defined as just moving one vertex to another. And in the same example, we can see that U or V is folded to U.
And here we have given a fold row that is surjective. We know there exists this iota such that these things occur. We also have a graph that is stiff if none of the vertices can be folded.
Which then leads us to the pleat of the graph G, which is the unique stiff subgraph. And in this example, we can see rho folds V to Y and W to Z. And then iota is the inclusion or the injective map of pleat G back into G.
So if we have a graph G, then the null of that graph is the automorphisms that are homotopic to the identity. So here we have a graph G, which is C4. We listed out the automorphisms of this graph, and then we drew out the null of this graph. So here you can see we have the identity, switching A and C, vertices A and C, switching B and D, and doing both switches, so A and C and B and D. And that is the null of G.
So here we can see that one of the first things we proved, if we have a series of spider moves labeled F1, F2 through FM, and those go from G to H, and if they're composed with the homomorphism phi, the spider moves or spider pairs are preserved.
And then similar to that last lemma we did where if we have the homomorphism and then composed that with those spider pairs, then the spider pairs are still preserved because they can only differ by at most one vertex. And if you compose that with homomorphism, they're still gonna differ by just at most one vertex.
So from there, we proved that null G forms a subgroup of aught G. And first we looked at alpha and beta in null G and both of those are homotopic to the identity. And from the previous lemmas, we can see that the composition of alpha and beta is also homotopic to the identity, and thus is in null G, giving us closure. And we can also see that the inverse of alpha is homotopic to the identity as well, thus being in null G.
So then we went and proved that it's a normal subgroup of odd G. So if we have an alpha that's in the null G and an X that's just an automorphism, we know that alpha is homotopic to the identity, and then we know we can do our composition, and then we get that X alpha X inverse is homotopic to the identity, which proves that it's a normal subgroup.
So we came up with a big question from our previous results. And so first, rho from G to plete G destroys homotopies. And this is because if it is a pleat, there are no folds available. So if there is a fold available, it's not a pleat. Then aught G mod null G also destroys homotopies. And this is because null G basically takes everything to the identity in the pleat. So the question arose, is there a relationship between aught G mod null G and aught pleat G?
So the first thing we looked at to look at that big question is if we have phi from spiderness to G of spiderness to G, is it an automorphism of the spiderness to G? So here we have our graph G, which is just our graph with the antennas, and we have the spider nest. So if we were to take like the automorphism CD and compose each of these automorphisms with it, you get something like CD composed with the identity would give you CD. CD composed with AB would give you ABCD. CD composed with ABCD would give you just AB. And CD composed with CD gives you just the identity. So you can see after composing all of them with CD, we actually still get those same four automorphisms. And the same thing occurs on the right-hand side where we did the reflection and then composed it. So those are all the automorphisms that are homotopic to our reflection. So if you do the same thing composed with CD, you'll actually still get those same automorphisms. Therefore, it is an automorphism of spidernest G.
So next we proved that if A prime is in aught pleat G, then A prime is an isolated vertex in the spider nest of pleat G. So we can see that each one of these are the automorphisms of pleat G. Being as it is, it goes to the identity in the spider nest. And then we have the option to reflect each one of these vertices across an axis, which gives us another automorphism. Or we can rotate, which gives us the final automorphism.
So one of our big theorems was psi gamma that takes automorphism G to automorphisms of pleat G is a group homomorphism. So we start with psi gamma A and psi gamma B, and we know that's equal to rho A iota, rho B iota, by definition of psi gamma. And from there, we get that it's homotopic to rho A, the identity of G, B iota, since iota rho is homotopic to the identity of G. From there, we get it's equal to rho AB iota, which then is equal to psi gamma AB. And from there, since we know that the automorphisms in the spider nest of pleat G are isolated vertex, then we know that psi gamma A, psi gamma B must equal psi gamma AB. Therefore, it must be a group homomorphism.
So looking at an example of that, we can see that we send G to pleat G with a rho. And if we are in the left-hand side of spider nest G, all those components will be sent to the identity of pleat G. And iota will map the inject or will inject pleat G back into G. So if we then compose with AB with iota, we still end up in the same automorphism in G. And then rho sends us back to the identity in pleat G. And then iota would send the same automorphism of pleat G back into G. Then if we do the reflection, we can see that we move away from the component that's homotopic to the identity in G, and we can see that any row that's composed with this now will be sent to a different component in the spider nest of pleat G, namely the component that contains the automorphism X to Z, Z to X. And thus we can see that psi of the reflection composed with psi of AB is equivalent to rho reflection iota rho AB iota.
So then our last theorem in corollary, we wanted to show that the null G is equal to the kernel of our psi gamma. And then we answered that question that we posed before, that the automorphisms of G mod null G is isomorphic to a subgroup of the automorphisms of pleat G. And so we have an example of this using that same graph with the antennas. We set rho to take A, B, C, D to Y. And so you can see on the left, in the left blue circle, we have all the automorphisms homotopic to the identity, and on the right we have all the automorphisms homotopic to our reflection. And so you can see that all the automorphisms in the blue circle map to the identity of pleat G. So they all map there, and since they are the null G, and they all map to the identity of the pleat G, then they must also be the kernel of our psi gamma.
So we have the same thing here in a little bit simpler example. Looking at C4, the pleat is just K2, and we can see that the left side of SNG is null G or null C4, and each one of those is mapped to the identity of pleat G once again, as there's only two components in SN pleat G. So everything that's in null G is mapped to the identity, and anything that's composed with the reflection is mapped to the other component. So we can see again that null G is the kernel of our group homomorphism.
So our last example here we have where rho takes C to A, and we can show here in our blue circle the black dots are actually all homomorphisms, so we don't actually we're not looking at those really at all. But we do have our two blue automorphisms, and they both also, because they're so AC is homotopic to the identity, it gets mapped to the identity of pleat G. So therefore, again, that's the null G, and since they get mapped to the identity of pleat G, they're also the kernel, therefore they're equal again.
So lastly, we want to say thank you to NSF, Kerm, Dr. Catherine Leonard, Dr. Tian Chi, Dr. Laura Skoll, and the research team at Fort Lewis College. None of this would have been possible without all of their support and guidance throughout the project.